Okay, we can go ahead and begin. To everyone on Zoom, if anyone just can give me a thumbs up that the mic is all working and it is currently recording, so that is all good. Thank you, Johan. Okay, so good afternoon, everyone, to everyone on Zoom and all you guys here. Uh, Happy Monday. I hope that you had a good weekend, everyone. So we have a few things to go over today in our today's lecture. Obviously, we have our slides, but let's begin first with logistics. So where are we at so far in the course? Currently, we're in week 4, and today we will speak about more of HTTP. We'll talk about cookies and caches and a lot of cool things. Then, if time allows, we will have an installation for Wireshark and a hands-on for Wireshark to give you an idea of how it works and what it is. That is important. I understand some of you might have used Wireshark maybe in other classes or you're just familiar with it as a tool, but this is important for the students that are not and can be referred to for everyone to go back to. So that is in terms of the modules where we at now. Um, for our assignments, just a few things to speak about, and specifically the Wireshark assignment. So I did not receive a lot of emails. It was just a few of you guys that reached out to me. I think it was 2 to 3, because it's the assignment was supposed to be released today, but I released it last Wednesday. So I figured that a lot won't start on it today, or I mean anytime soon. But there is a slight revision that needs to be done with the assignment. If you have not started the assignment, as of now, you do not need to worry about starting it because it is under revision right now, and it will be after it will be revised. It will it will be republished. But basically, what it is for the students that are that did start on the assignment, there is a few you would say hassles in the assignment. One thing is that the link, this second link right here, is no longer directing you to Ali Web. It takes you somewhere else. So that is one thing. And it uses HTTPS, so they added TLS. And then our other website, which is DP Graph, it's also encrypted. It used to be HTTP, but now it came HTTPS. So that's why the assignment needs to be revised. So there is no worries for the students that started on it. Just bear with me that I'll revise it very soon. And I will upload the announcement again for it. And you can start on it. I'll also extend the deadline. Currently, it's due at, when is it due? Due September 21st, obviously, but we have the late policy for the students that submit late, but it will be expended beyond that. So that is it. We have the assignment covered, where we are so far, and now we can dive into our lecture. So let me do this. Okay, on Zoom, let me share my screen. I believe it's good. Yeah, okay. Let me just move this up. Okay, so currently we're week 4. We're still in the application layer, and we'll be in the application layer for about another week or so, because there is a lot to cover from it. Last week we spoke more about the application development of applications, and we spoke about a little bit of protocols. We dive into the HTTP protocol, but there's more that goes to it. So we're just gonna finish the application layer in terms of as a chapter, but we will continue on HTTP and the web. As I have to mention this in every lecture, the class is recorded, and I know that we are not using. What do you guys prefer more, Zoom or Panopto? Doesn't matter? Doesn't, are you familiar with Panopto? No? You? Yeah. So you used it before? Hmm. Okay, a lot of people in the chat preferred Zoom. And to be frank with you, since this is a class that's offered in two sessions, we were trained and we are supposed to use Panopto, but I don't know, I stayed away from it. But the cool thing about it is that say for example, I'm working on both machines, and the class is recorded and knows that the input has switched so that when you're watching the lecture, it switches by itself. Here on Zoom, it's a little bit different. So that's why I'm using my laptop and presenting and doing the hands-on from here. As you know, Wireshark may be a little bit of problem to install on here on the UCF laptop. But yeah, we will continue with Zoom. There will not be an issue with that since you guys like it more and it's efficient. Okay, so for the lecture objectives, we're going to review HTTP fundamentals. Last lecture, we talked about requests, and we gave an example of a request from the HTTP protocol. Today, we'll look at the structure of the request and response again. We'll talk about non-persistent and persistent HTTP connections briefly. And now we will dive next into cookies across the client and server and note some privacy concerns that do come with that. We'll also understand the role of web caches like proxy servers and reducing delay and how they can be very efficient. We'll also describe Git and how it avoids unnecessary transmissions. We'll look at the four different requests when it comes to HTTP protocol. And then we'll talk about HTTP 1, 2, and 3 and talk about the differences and why they exist. So currently we're in the application layer. We talked about principles of network applications. Now we're still in web and HTTP. So let's go ahead. So this is just a recap from last lecture. This will get you going for today's lecture and to keep you refreshed. So we know that a web page is not just a single file. It's a collection of objects, and those objects could be other pages, other images. So the HTML file defines the structure of the page and reference to other objects. So a URL, we know it contains two parts. First thing it contains a host name, and that is basically just the name of the website, and that's also kept by the DNS as well. The path name is that we have here, some dft/pic.gif. So that is it. So when you request a single web page, your browser makes multiple requests based on the object that you have in the website. So a web page is the base HTML file, and then the multiple objects are all fetched into the via their URL. So this is the idea of web and HTTP. When it comes to looking at how the HTTP works, that the communication happens using the protocol HTTP, and we have an example here. That in the diagram we have two devices that are running. We have a PC and an iPhone. So for the server, it is that we know it's a machine stored somewhere on the internet. And it stores the website and the data. On the bottom left, we have two clients, and this is a client to server model. The client starts the conversation when they type http.example, and the browser sends a message responding saying, hey, I acknowledge this, and then the server responds. And it's the same thing for the iPhone. Now, this gets repeated back and forth depending on the objects that you want. So the takeaway is that the web page is a simple request response cycle. Clients ask the servers for something, and the HTTP is a protocol, means of a language that makes all this possible. Now, so we know what HTTP is. Now we have an idea of it. It does not work alone. We know that data confidentiality is important, so that's why we use TCP. The reason that TCP is reliable, different from UDP, we said that the TCP has an acknowledgement that goes back and forth. UDP does not. Um, Something to know with HTTP, we know that it is stateless, meaning that the request is separate and independent for each object or for each initial request that you do send to the server. So when your browser accesses the server for one web page, the server does not remember that you asked for another page earlier. And today there will be a way that it kind of remembers that what you were asking for. So why is it stateless, and what is the use of making HTTP stateless, or why is it already set as stateless? Because remembering history, like keeping state, make things very complicated, where that the server has to keep track of every user, and it suddenly crashes. There could be memory of those interactions, could be lost or mismatched. So the state of that is difficult. So to keep it simple and robust, we said that it is stateless. So as a wrap up, two takeaways here. HTTP rides on top of the TCP to deliver a reliable, guaranteed delivery. And HTTP is stateless, but which makes it simple, but also requires extra tools like cookies when we talk about persistence. And we will dive into cookies today. Now, with persistent and non-persistent, to give you an idea and a recap, with non-persistent, meaning that every time your browser requests something like an image or a style sheet, it has to open a new TCP connection. That means a web page, like we said, with 10 objects might open 10 separate connections. This creates an extra delay. On the other hand, we have persistent, which is more efficient. It keeps the connection open. The browser can send multiple requests and it gets multiple responses back. That reduces the overhead and makes loading much faster. So persistent HTTP is more efficient and is what most browsers are using today, which is HTTP 1.1. So the main takeaway is that non-persistent is per object. Persistent means connection for many objects. And one of the questions that arise from last lecture is how does the persistent know when to close the connection? Like the connection gets open for the objects that we want, but when does it close it? So reading about more in this in detail, usually it keeps an idle time such that gives yourself like 10 seconds. If there is no response from the client, it shuts down the connection. So that's the two connections that we have with HTTP. And here's an example that we see here. Step A1 enters this URL link, which is someschool.edu. And this link has 10 pages. So what happens first? Initiation happens from the client, which is in 1A, and it initiates a connection to the server, which is the website that we see up there. The server responds saying, "Hey, I have accepted your connection from the client." Then we are now ready to communicate. So then step 2, what the client does is sends the request message asking for the HTML base of a file of a web page. And then the server sends a message back saying, "Hey, I got your request, and here's the file that you wanted." But here we must know one thing. Within the link, we have 10 JPEG images. So these are 10 individual objects. So with non-persistent, a new connection happens for one image at a time. Okay. Then what happens after that in step 4, the server closes the connection after sending the file in step 3 because we know it's non-persistent. So the connection closes per object. Now step 5, the client received the response, like the base HTML page, and the browser parses the HTML and sees that it does contain the reference to the image that it wants. And then step 6, it says that it gets repeated per object. So if we have 10 images, this process would repeat it 10 times. So that is an example of non-persistent HTTP. Now, non-persistent, continuing on non-persistent, we also must keep track of time. And this is something that is very important in networking, in any task that we do, like whether we're assigned a task from our manager, there's a time on it. Time constraint is included in everything. So with non-persistent HTTP, we have the round time trip, which is basically the time for a packet that gets sent from the client to the server and back, right? So you can think of it as like the network latency for one round trip, because we know we are doing one trip for non-persistent per object. So here's an example that we have here. To fetch one object over HTTP with non-persistent connection, the response time includes several things. So we need one RTT to establish the TCP connection from the client to the server. And then we have another RTT here for the client to send the HTTP request and receive the first byte of the response. We also have to keep in mind of transmission time. And this is for the server to send the entire object. So here in the figure, we have the client initiates a request that costs one RTT, and then the client request file waits for the server response. That's another RTT, runtime per trip. Then finally, the file is transmitted, which is shown in blue here. So the takeaway from this slide is that for each object with non-persistent HTTP, the total response time is about, we know that, 2 round time trips plus the file transmission time. Okay. Here's a little bit more about non-persistent and persistent. We know that for non-persistent, it requires 2 RTT for setting up TCP and for the request and response, as we've seen in the previous examples. There could be an overhead with non-persistent, such that we are opening and closing many TCPs that consumes a lot of resources from both the server, the client, and persistent is one connection that is open for all the objects, for all the requests, for all the responses to be reused on the same connections. So it is more efficient. It is less overhead. There is no need to repeat the connections for every object. And clients can send multiple requests without waiting for other responses. So it is much faster overall and making the page loads more efficient. Now, here's where we left off last class, right? So we said that with HTTP and with a client and server, there's a request and there's a response. So we're going to look at the request first. And the request is very human friendly. If we look at the picture, it depicts many things, and we can read many things from it without needing to know all the details. So the first thing that we need to notice is that the request message begins with a request line. It could be get, post, and we will talk about the variations of HTTP request lines today. This one has get, which is basically it wants to get a specific web page from the server. It also includes the URL. In this example, it's index.html. And it talks about the specific version it includes, which is H1.1. And the line ends with a /r/n. That's an indicator that the line has ended. Okay. After the request line, which is the first initial line that we see, we go down to the header lines, and these carry additional details about the request. It talks about the host being contacted. And the host in this example is University of Massachusetts. Okay. Also talks about the browser that making the request here. Talks about the type of objects that it wants, preferred language, whether the connection should be kept alive or not. And this is part of your Wireshark assignment, to know that given a website, when we analyze it with Wireshark, do we want to know is the connection kept alive or not? And then the message ends with a blank line. And this marks up the end of the headers. So the structure is very straightforward. Now, more on the request message or the format here is just like the structure without the example that we have. We still have the request line, That's the method, such as get or post. And it talks about the URL we want and the version. After that, it comes the header section, as we've seen in the last slide. Each header is written as a pair, a field name and its value that is separated by a colon. It talks about the host, as we know. It talks about also the browser, which browser it is that the host is using. And then finally, the request includes a message, which is the body. And usually some requests, you might not be able to see the body, such that if it's encrypted, then you cannot really see the data that is that is getting requested. But the data here that we see, which is the body, is the data that's being carried from the client to the server. So when you submit a form online, for example, let's you're going on Google Forms, I think, or if you're taking a survey, the data is included in the body of a post request. And not all requests carry a body, because based on the method that we use for the HTTP request, it might not be there. So methods like get usually don't, but methods like post, because when we use post, we are filling information in. And we will come more into this. So the structure is clear. And just one more thing about this slide, when you see that SP or CR or LF and the diagram is it's just used as separation, separating fields. And CRLF and means it marks the end of a line. That's why we see it with the request, the header, and also before the body begins. Okay, now we have an idea of get in the last example, but as we said, there's common request methods. The first thing is post. It is used mostly when a web page has to form a web page has a form to collect input from a user, and then this information or this data is stored inside the body of the request. So, for example, you are filling out a survey, you are applying for something that gives you an idea. So that is for the post. Now for get, get is usually for retrieving data, but it can also send small pieces of data to the server. So instead of having the whole body, like we have in post, the data is added to the URL after the question mark. So as shown in the slide here that we have an example of some website, somesite.com/animal search monkey banana. The input values here are monkey and bananas. That's the part of the URL itself that we are trying to retrieve from the main path of the HTML website. Okay. Next, we have also head and put. So head works just like get. It is very similar, but the server only responds with the headers. It doesn't give you the actual content. It doesn't give you that much details. It's useful if we want to check if something exists or information like update or without downloading the full page. Lastly, we have put, which is if a file already exists in a certain path. To recap on put is used to upload a new file, like an object, to the server, or completely replace an existing one. So when you go and replace your LinkedIn image or your Facebook image, you're using put because you are uploading an object to the website. If the file already exists in the path, then put will overwrite it with the new content provided in the body of the request with the new time that the put method has been initiated. Okay, so these are all HTTP request messages, and we will, when we do a little bit of Wireshark today or with your assignment, depending on the website, you might be able to capture some of these request messages. Now we talked about the request, what it entails. Now let's look at the response that usually the server sends back. um, to the client, ideally. So in this picture here, the response has three parts that we should be aware of. We have the status line, we also have the header lines and the data, the body, right? So the first line that we see, which is the status line, indicates the version that is being used in HTTP. Here in this example, we're using 1.1. The status codes that we will talk about, various static codes like 304, I believe 400. So each status code has an implication, meaning this status code here, 200, is a short status phrase for like, okay, yeah, the response is sent back, okay, everything is fine, back to the server. This tells the client whether the request succeeded, failed, or needs other action. So, going back to a little bit about the Wireshark assignment, when the websites got one of the websites got moved forward, it could be one of those actions that were there. So you're requesting a specific website, but the response that you get as a status code might be not 200, like not okay. The header lines is we have a series of headers here. These gives extra information about the response message. In the example that we have in the slide, we see that the date, which is Sunday, September 26, 2010, a little bit outdated. The server type that we have, the last modified date on the file, which is October 30th. So they're very easy to read. You don't really need any sense of knowing that information. It's just very straightforward. Also, it talks about the content length, and which describes the size of the format of the data that is being sent, and then other details like would the request or the response of the connection should be kept alive or not. That is included in both of them. Data, we said that it's the body response of a message and the actual content that is requested. For this example of the client requested a web page, this is where the HTML file is returned. So in this slide, it's represented as data, 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 but if it's an actual example, then this will be replaced with something else. So overall, the response message starts with the status line, continues with the headers, and ends with the actual data. Now, we talked about the status codes such as 200 OK, we've seen in the example. But the first line or the first response that gets sent back from the server to the client is the status code. This tells the client whether the request was successful or failed, and based on these static codes that on the status codes that we have here. So the first one is 200 OK. That means the request has worked and the requested object will be sent later in the message. 301 means it moved permanently, meaning that the requested object has been moved to a new location. That could be a possibility. The new location is provided in the location field of a response. So that is part of the response, message. 400 bad requests. This means the server could not understand the request message that is being requested, usually caused by something like invalid on the request. And to give you an idea, a little bit of hands-on and real world, during my research, when we worked on whether to classify the applications if they're malicious or benign, we would obviously send the hash function of each application that we have to the virus total, and then we would get a response from the server, which is virus total. And these codes, status codes, tell us, hey, this request has been accepted. And also, a few things to keep in note is that we have to, well, and in my project, that you have to keep a time between each request that gets sent, such that the server does not get overflown. So that is just to give you an idea. We have 404 not found. One of the most codes that you'll see means the document does not exist in the server. And finally, we have 505. HTTP version is not supported. This means that the server does not support the version of HTTP used in this request. Um, Now we will speak about cookies, but I think this is a good time to stop and do a little bit of Wireshark uh, to give you. We're going to do a simple Wireshark installation and a simple lab about HTTP requests in that. And we know that Wireshark can be used for various things. It's a packet analyzer, packet sniffer. We might have some files that are available by maybe for research use, and we can do a lot of analysis on it. Like maybe we want to read the body of the data or something like that. But today our focus is relatively close to chapter 2, the application layer, and specifically the HTTP protocol. So let me get out of this. And I know that it has been stopped, the request, the sharing. Let me just reshare it. Okay, let me share my screen. Okay, first thing first, if we go to the modules tab, and initially what we will do is an installation of Wireshark. This is to make everything clear, and we have the right version and installation and all that. So there's a file that's uploaded from last week, and we also have this Wireshark intro. And okay, perfect. Let me just reopen these. Yep. Need that anymore. Okay. Put this one out. Let's download this very quick. And then we have that. Okay, so let's start with the installation. Now, in this guide that has been uploaded, depending on the operating system that you have, there is a guide on how to install it. So first thing first, because I actually have Wireshark currently, I will just very quickly go ahead and install it so I can show you the installation process from the beginning. Um, if we go to the control panel, installer program, and we have Wireshark. Just want to install it and install it very quick. Okay. So now it should be gone. Oh, does it still exist? I don't think so. Yep, delete the shortcut. Okay, so first thing is we're gonna put this to the side and this here. We're gonna open this link. You can either click the link to take you to it, or you can just search for Wireshark on here. Either way will take you to the website. So after you come here, and now this is going to be based on your operating system. For me, it's going to be Windows, and I don't have the ARM architecture, so I will directly just download the 64 bits. So let's download it here. After it finishes downloading, we will open it. Give them access, yes. Okay. So this is the next screen that you would see within Wireshark. So just click next. We don't really, there's a lot of installation features that do come with it. We're just gonna install the plain version that is there. So this is, I think, their license agreement noted. Your donations. I'll donate later. Okay, so yeah, these are the components that we are talking about, and I think for our class, we will not be needing anything that is explicit in within one of these. So we can just click next. Here, if you want a desktop icon, you can do that. And then, yeah, this is for the association of extensions, like that happen. Here, simple, choose the folder that you want to download it to. This is very important right here. So when you get to this tab, obviously because I just have installed it, so NCAP 1.80 version is already installed on my device. But if you are installing it on your local PC and it's your first time, make sure you do check that NCAP installation. This allows us to capture and to analyze those packets that we do have. So that is important. USB cap, I don't think we will need that. Just click install. While this is installing, the same thing goes for the Mac. You have the direct link. It's a little bit different with Mac. I don't think it's that much of a difference. You have to download this package. And here we will get into, after it downloads, we will get into a little bit about the navigations, what it is, how to easily navigate through Wireshark, and then we'll start our lab one. So far, does everyone have it installed? Yeah. Okay. It should be very straightforward. I think to install it, it's not difficult, and there's a couple of videos that are mentioned in the assignments for guidance as well. Okay, that's it. So after it installs, this is where we're gonna see. Okay, I want to go to this picture specifically. So if you're not familiar with Wireshark and you don't know how it exactly works, in our outside model from a top-down approach, what Wireshark does, it's basically a packet analyzer. Once it gets to the link layer, what the Wireshark does is it takes a capture of the packet, and this is usually called the PCAP file. So that is the idea of how Wireshark works. Okay. Now, when you open it, your home screen should be something like this. And as soon as you click Wi-Fi, it's going to start capturing. So you got to stop that. Um, so if you're not familiar with it, this is your screen. On the right pane. You're going to have your hexadecimals that it shows here. Your top pane is basically all the main header rows, titles. And your middle pane is the data that it shows. So looking specifically here, the top pane shows us various things. It shows us the number of packets. So in the matter that I started it till I stopped it, has a lot of packets, over 1,000. So that is the number of packets. That is the time when the packet was captured. We have our source IPs and our destination IPs, and a very nice way to know your IP or know the destination IP just is to quickly ping it. You will get a response. We have the protocols like TCP, UDP, and other cool things that it talks about the length, a little bit about the info. The length is basically the size of packet in bytes, and info is just like a description of the contents of the packets as an overview. And then here is the middle pane. We have this is obviously UDP, so it's a user datagram protocol. It gives us the port numbers and various things. So I think we can start with our lab. This is just the installation and how to download Wireshark and how to navigate through it. Once we start the lab, you will know a little bit more about it. So we spoke about Wireshark, how it does the work. Now we will do a demonstration. So you can follow along right now or at home, but this will be there. So start up the Wireshark packet sniffer, but don't begin the packets tracing. And basically to start tracing, you would just click the blue button here. And then to stop it, you would just stop it to stop it whenever you want. But ideally, you do not want to capture for a long time unless it's something like more intended for it's really based on your use. But for your assignment, you do not need to capture for more than a minute per se. But to give you some tips, before you start capturing, what you should do first is you should clear your browsing cache. So if you, let's say you worked on the assignment and you accessed the browser on a Monday, and then you did not finish the assignment. When you come to complete the assignment on a Tuesday, you might not get some of the status code responses such that it has already, you already have kind of requested. And when we complete the slides, you will know more about what I'm talking about. So just make sure that you're using a different browser or clear the cache of the browser that you are using. Okay, so okay, and then here usually it says when you begin Wireshark, wait a minute, you'll see why, and this is generally what shows you have to stop it. It captures a lot. So here's the cool lab that we will do here in a minute. So I know I have a lot of things going on, which is like the Zoom, I have various tabs. So we might capture packets outside of the intended of this website. But the first thing we will do is we will start capturing, which is we click a new button. You will see that you have unsaved packets, and when you save those packets, it turns as a .pcap file, such that you can refer to the file again to reuse or to analyze those specific packets. So if you analyzed on a Monday and you're coming on a Friday, you can look at what you analyzed on a Monday. So that's that. Here we're not really we don't really care about this, so we'll continue without saving. We'll start the capturing. We'll access this link. It says congratulations, and then that should be fine. We can stop it now. Going back to here. Let's see what we have next. So obviously after you stop the capturing, you should see these number of packets that you have captured. And we did capture a lot because we have various things that are going on. So what you do first is you find your IP address. And if you want to find the IP address of your device or the destination IP address, a very quick way and a simple way is if you go to your CMD command prompt, and here I'm on Windows. This Zoom thing is really annoying. Okay. What's going on? Okay. So what we can do is we can ping the website that we have. So if we go back a little bit up here to find your IP address, you can do IP config, and that gives you a bunch of things like the subnet mask, IP version 4 and 6 if it's dual booted. But here's typically our address. You can also do IP config / all. That gives you more details, like the DHCP, which assigns IP addresses dynamically. But so this is the idea. But to know the source IP address, what we can do is we can do ping. And we don't need to specify the whole, we just need to specify the path. We don't need to specify the HTTPS. So we just get directly into it. We write that this is a website from the lab that we have. So that gives you an idea. This is the IP address of them. This is pinging. Also with ping, you can see if the request is successful or not. So we will go ahead and stop it, but this is ideally, it gives you a general idea on how to find the IP address of the sender and the receiver. Next thing that you do when you come back to Wireshark, and as an analyzer, you do not want to spend a lot of time analyzing. You have to be kind of efficient with your time and how to get something very specific. And the filter here on Wireshark, it is very neat, depending on your use. So in this assignment, we're looking at HTTP protocol itself. And it's basically going to be running from the server, a client and a server. So the first thing that we do, we want to know is, do we have HTTP protocols in what we captured so far? So we just go to Wireshark, we type in HTTP, and some of these I already, because I was working on stuff, but you see that we have two HTTP requests, and one of them is the website that we have open, such that we are requesting this website from the server. Here we have something else, which I'm not sure of. But to go back to the ping, and you can cross compare between the IP addresses, they should be the same with the Wireshark and the ping. So that is the first thing you can do to find HTTP protocol traffic. We also have TCP, which is more in the network layer, not the application layer. If you type TCP, you get a bunch of TCP traffic. And we know that there could be variations of TCP such that it uses TLS, because TCP is the vanilla, the protocol. TLS is an additional add-on. Also, we have the DNS. So you get the idea, you go here and search. Once you get a red, that means this specific criteria or this filter that you're implying is not there. So when it turns green, that means yes, this is accepted. Okay, that's to find specific protocols. Now, another way to analyze is based on the IP addresses. Since we know the IP address, we can just directly look into the packets or the capturing of that specific IP address. So here's one cool filtering that we have, and you don't need to remember any of these. You're just a quick search away from them. I think AI does as good, and Google. So here we have the web, the IP of this address, and what we can do is we want to see the packets with this IP. So we do IP.addr equal sign. Oh, there is an issue. Equal sign 192. Okay. 128.119. And then you hit enter. So this is the packets with one IP based on the IP that we just entered, and you can change it to however you want. You can put the destination IP or the sender IP, receiver, vice versa, whatever you like to do. Another cool one when searching with IP addresses that we have is, let's say you want to find only the Intel capturing of a sender or receiver, so we just put both of the IPs that we have. So the IP of this website we have in our lab is this directly, and our IP address should be the .214, I think. Yeah, that's yeah. So what you do is on the same thing, you just put two of these characters, and then you repeat the same thing again. Sometimes you might have to flip which comes in order, but we can try and see. 2, and we put our IP address 10.
32. 38.
Mhm. Okay, there we go. So because we did capture a lot of a number of packets to get those specific ones that we want. We do from the source to the destination, from destination to source. I don't think there should be an issue with that. So we see that there's HTTP, TCP. Now a little bit that we can go into. Yes.
What order is it for this to make first for this one?
Currently,
Yeah.
this one is the source I have. I mean, the destination. Sorry, yeah, and then this is our source. So I don't think there should be an issue when you flip them. You don't have to keep them in order.
Oh, it doesn't matter. It doesn't matter.
It doesn't.
As long as you address it correctly. As far as like the IP address equal, but it doesn't matter if we have it either way around.
Doesn't matter, yeah. Thank you for that. Okay, so to look, because we looked at the slides today, and maybe what we can do is go back to them a little bit. I just want to show you that the response and the request message that we talked about today. So to view the data or to view whatever packet you want, you can double click on it, and this gives an expansion view with the hexadecimal view. But here we're looking at the HTTP, the Hybrid Text Transfer Protocol. And we can see a lot of things. Get is one of the commands that we use for one of the requests that, as we discussed. Here's our website that we requested, the HTTP version, who's the host that's kept by the DNS, is the connection kept alive, that means it's persistent. The agent, it gives you a lot of things. I'm using Chrome here. It also talks about your language here, accepted language, and various things. So actually, the assignment is very easy for you.
Yeah.
It is very easy for you now to do the assignment. It's if you go back to the lecture. But ideally, what we want is for you to know and to get an idea hands-on. But that answers a lot of the assignment. But do not worry, I will not change the questions. It's just going to be change of the links. Okay, we can close this. A couple of things that you can do is a few tips. Once we have like a TCP protocol, what we can do is we can right click, and we can click follow and follow the TCP stream to see, because we know with TCP it's a request and acknowledgement. So this gives you like a detailed insight of the TCP requests. We talked about the filter colors. If it's green, it has a problem. Is it case sensitive? Yeah, it is case sensitive, so just be aware of that. We said that when it turns red, that's mean invalid, green is valid. Also a cool way what you can do is for the time, you can click view display time format, and you can change those to the second, first, seconds since the first capture of the packets, the previous. You can do day and time of day. It's whatever you want. So these are just additional tips. And if you watch a lot of resources and videos, you can find a lot of cool things that you can do with Wireshark that enhances your analyzation phase, I would say. Um, and then here we have the same headers get repeated for everything that we do. So basically, that is it for our lab of Wireshark. We have about 20 minutes left. So to clear out the display filter, you can either erase it or click here. And so you see that when you start capturing again, it's going to give you the same request message. So just be aware of that. If you already did the capturing for the websites of the assignments, just save the file. If you click save, I think it directs you and it gives you a results.pca.png. And then you can just go ahead when you come back and just open the file, takes you back to the same thing.
David Bumble is pretty good. Christian.
David Bumble.
Yeah.
How do you write his name?
Bumble.
B-O-M,
Yeah.
like that?
Yeah. Why? It's pretty good. It's really good.
Ethical hacking. I mean, obviously, don't do this
Yeah,
in public.
don't do that.
Yeah, he has it.
Every
Yeah, it says he has a lot of videos, so I can, yeah. So if you're more interested, aside from doing the assignments and want to look into Wireshark, it has a lot of cool things. I think if you take any graduate classes, you can do like password cracking, password guessing, reading info that is entailed in the body. But that is it for Wireshark. Let's close this. And let me just stop sharing very quick. And we will get back to let's close this out. Okay, let's continue with what we have. We might be able to finish this, maybe not, but we will see how we progress. So next thing is we talked about the HTTP protocol. We talked about various things. The next thing that we'll discuss about is cookies, which tells us the result of the request. So the HTTP response tells us the result of the request. So that brings us to our question is, how do websites remember us across multiple visits? And the answer is cookies, obviously, right? We know that HTTP is a stateless protocol, and we mentioned that a lot of time, meaning each request is independent. Okay. Okay, that's good. So to get around this, what websites do usually is they gather cookies to maintain state between interactions. So there's 4 components that we should be aware of when it comes to cookies. The first thing is the server first, what it does is sends a cookie, a header line in the HTTP response message. On the next request, the client includes the cookie in the request message. So the client, the cookie message or specific ID for that cookie goes back and forth. So the cookie itself is stored on the user computer, managed by the browser. That's why you sometimes, when you access some things or recommendations that you get, it tells you, hey, go delete your cookies, clear the cache, all that stuff. So they keep related information back-end system to identify or track the user. This could be a privacy concern. So, and the use of cookies is for various things, to remember things like login sessions, shopping carts, or user preferences, such that if you go and delete your cookies, when you go to log in again, you have to log in again, that it does not remember your login info. So here's an example that I have of how the cookies do happen from a client to server. Here we do have a client, we have a server, and we have the backend database, right? So on the client side, we see a cookie file already containing an entry for eBay. Um, this shows that the browser can hold multiple cookies from various sites. It does not mean it holds a cookie per site. It can hold multiple. This example, we're going to talk about Amazon cookies. So as of now, there is no Amazon cookies because there is no initialization of the request. So first thing that happens is the client sends a usual HTTP request to Amazon, which is Amazon basically as in terms of the server. The Amazon server replies and gives an indication or includes a set cookie number, which is 1678. This means Amazon is creating a new cookie ID for this user and adding it to the cookie file. Now the file contains both eBay and Amazon. On the server side here that we have, Amazon also creates an entry ID for the back end of the database based on that cookie number. So what we have here, the next time the client makes a request to Amazon, it includes the cookie header 1678. This lets Amazon recognize that the user is performing specific actions like personalizing content. The server replies with a response. Okay, so even a week later, the cookie's still in the browser and with the same specific file for Amazon and eBay. Unless we delete the cookies, then that is a user. You would say it's really much up to the user. So when the client visits Amazon again, it automatically sends the same cookie that we have. Then Amazon looks at the server, looks up that cookie, specific cookie on the back end database, and it remembers that this is it. So that's why when you go to Amazon and you're shopping and you look at you order a bunch of things, you put them in your cart. When you come back another time, they're already stored there. So let's summarize what cookies are mainly used for. They can use for various things, authorization, remembering that you logged in into a site. Also shopping carts helps us keep track of the items before you check out. Also gives you recommendations. That's why when we access something in our phone or our PCs, we see a bunch of ads in our social media. And it's a user session state, meaning that it keeps your email session open while navigating through different pages. That's also that. But that also brings a challenge is with cookies is that how to keep state. Since we said that HTTP is stateless, we need to carry the state across multiple transactions. So as the protocol endpoints like the server and the sender and the receiver, or browser and server, both need to maintain the state over time. In practice, cookies, like what they help us with is they carry out the state of the information that we do have. So it's important to know also, like we said, there could be a problem with that because it learns a lot about you and your activity on the website. Some of us, we don't really care about that. We're just going on Amazon to shop. We don't care about what they take, but there is some, I'm not, that's why I look back at you. I know it's a little bit sensitive to you, but some are very crucial of what happens. So this is the idea of cookies. So yeah, it could be a privacy because your identity can be tracked and followed through multiple different websites. Now, web caches or proxy servers is what helps us maintain the issue with having cookies and HTTP being stateless. Here what we have is proxy servers, and the main goal is to satisfy the client request without involving the original receiver, the origin receiver per se. So it works in a way that the user configures their browser to send HTTP to a web cache. And when a request arrives at the cache, there are two possibilities that we do have. If the requested object is already stored in the cache, as we see here, then the cache sends it directly back to their client. If the requested object is not in the cache, then it goes to the origin server. So when we're requesting ucf.edu, you can assume that a lot of students are requesting that page. So it is stored in the proxy server, and it gets sent back without going to the origin of the server. So when the origin server responds, the cache stores a copy of the object and then returns it to the client, so that let's say a new user is requesting this page that has not been requested by any user before. You make a request, it is not in the cache, it goes to the origin server, it responds to you, and then it also keeps a copy in the proxy server such that when a new user requests, it is very so the goal of this is basically to be efficient and save a lot of time without the repeated trips that we do need. Proxy servers are used both in persistent and non-persistent. It does not really matter, because each persistent, if you request an individual object, then if it's stored in the cache, then it is there. For persistent, it stays, the connection remain open. If it's non-persistent, then it gets repeated. But if that requested is in the cache, then we are that is fine. So it works for both. So a little bit more about web caches, like proxy servers. It can act as both client and a server. It is a server for the original requesting client because it delivers content directly to them. At the same time, it acts as the client to the original server to fetch information that is not stored there. So typically the web caches are installed by the internet service providers, like universities, companies, or residential internet service providers. So why do we use web caching? Three main things: it reduces the time, it reduces traffic, and since the internet is dense with caches, it allows simpler or poorer content providers to deliver their content more efficient, because the cache help distribute them closer to the users. So here's an example that we have a little bit of about a scenario of a caching example. So how do we quantify the performance? Looking on the scenario here, on the bottom we have an institutional network, and we got a public internet where the origin servers live. So the access link rate we have here is 1.54 megabits per second, and the runtime trip to the server is 2 seconds. Each web object is 100 kilobits in size, and the browser that are requesting the objects has an average rate of 15 per second. This means that the total data range going forward to the browser is about 1.5 megabits per second. In terms of the performance, when we talk about the access link here, the LAN utilization is very low. It's only 0.0015. So the local network is not the bottleneck here. The access link utilization is extremely high at 0.97. This means the access link is mostly saturated. So when the utilization gets high, we have larger delays, obviously. And the end-to-end delay can be broken down as we have the internet delay, we have the access link delay, and the LAN, also the local delay. So in this case, as a result, A equals 2 seconds plus minutes plus microseconds, showing that the biggest delay is caused by the nearly saturated access links. And this is what helps with proxy servers, and we will talk about it more. The problem is with this currently right now that we have is that high utilization on the access link, the delay increases very big drastically. So what we can do, what can we do to improve the performance of this? And one option is to buy a faster access link, is to reduce the delays and upgrade the access link that we can do. So in this access link here in this example, it is increased to from 1.54 to 154. The round trip time to the server, the object size and the request remain the same as before. The average data rate to the browser is still at 1.50. So with the faster link, we do see an enhanced result, but the main drawback is the cost. Buying a faster access link is effective, but it is expensive. So there is another option that we could look into. And here's the idea of what caches, how it works in all of this. We know that one option is to buy an access link. One option to reduce the delays. Another option to reduce the delays is if we install a local web cache inside the institutional network. We have a lot of workers, they request or do more of the same thing. We have a web, when the request goes, it does not need to go through the access link to the origin servers, such that it is stored on the local web. That's why they are responsible for installing these. The institutional, the college, so whoever is. So here, the access link rate, the object, web object size, the average request from the browser to the server remains the same. Those are not gonna get changed. And the key benefit of this here is that the cost, in terms of cost, it is cheaper. Installing a local web cache is way cheaper than upgrading to a higher or better access link. And I think this would be a good time to stop to install how to install a web cache. What we can do is we can pick up on Wednesday. And as I said, the assignment will be revised soon, so please bear with me on that. And if you have any questions, email me, please, the TAs, office hours, any of that, okay? So thank you to everyone on Zoom. Take care of yourself and have a good night. Okay, sir, have a good one.